All right. Good morning, ladies and gentlemen. Welcome back to the last week of your favorite class. All right. We're in it. Last week. Yes. Almost done. Couple of announcements quick. I did have this up, but maybe I'll put it back. Today's agenda, we're going to finish sandwich structures, what I can do. I would like to have talked about sandwich structures a lot more, but complicated. We'll talk about why they're complicated in just a second. But we'll talk mainly about manufacturing methods today. Your homework number 7 is due on Wednesday. That's on woven composite materials. So you should be able to do that right now. I think a pretty straightforward homework, a couple of qualitative questions, and one what I think is a short workout question. So just bang that out quick and get that in by Wednesday. All right. Final exam study guides posted. That's what we'll talk about on Wednesday's class. We'll do a kind of a final exam review throughout the day. So I'll bring that study guide up. We'll go over it just like I've done in the past. And then your final exam for this class is this upcoming Friday at 8 a.m. So set your alarms, do whatever you got to do, get your mom to splash water in your face or whatever, so that you're awake and ready to go 8 a.m. on Friday. All right, it's going to be a 50-minute test, just like before. Get there early, point your camera at yourself while you do your work. Open everything just like normal. All right, how do we like the meme today? Effort of many scientists, great technological challenges, all this to deliver an internet to Billy. The Earth is flat. Yeah, it's ridiculous. I particularly like his T-shirt down here too. It's like a boat falling off the side of the Earth. I don't know if you guys caught that, but oh man, it's funny. Good comic. Good comic. All right, so back to reality. Man, I wish I had more time on sandwich composites. I really do. All I'm going to really have time to do today, talk about their mechanics, is say why we can't apply previous theory to these sandwich structures. All right? It's unfortunate, but that's the way it is. I would rather focus my time on some practical things like manufacturing aspects than maybe the math behind sandwich structures, since the math behind sandwich structures is really blown up because of our classical lamination theory has one particular basis or assumption that we make that does not hold for sandwich structures. So basically all the classical lamination stuff that we've done so far does not apply for sandwich structures, which sucks, but that's the way it is. So I had this internal debate with myself about well, do I spend a week sort of redriving all of the lamination theory that goes along with the corrections that are required for sandwich structures or not? And so that's why it kind of took me a while to figure out what I wanted to do with these sandwich structure notes, because did I want to dive in on that new theory with the shear correction? That's what we're going to talk about today, or not. So I decided against it. I decided to do fraction mechanics and cure kinetics and some of the other things that sort of I think are a little bit more practical and useful and in place of sandwich structures. So I'm going to have to just gloss over some of the mechanics associated with sandwich structures, but the big takeaway and the big thing that you need to know is all of the classical lamination theory that we talked about at the very beginning of this class, so the first basically 5 weeks, no longer applies to sandwich structures. So it's too bad, but that's the way it is. And I'm going to explain quickly why that is, and what assumptions are sort of lost that cause us to lose this classical lamination theory idea. All right, so I'll put you back over on the whiteboard and let's talk our way through it. All right, so we were talking about sandwich structures. I'm just going to bring pictures of sandwich structures back in here. Hopefully you're not hungry talking about sandwich structures. Not the kind you eat, the kind that are made out of composites. I did not have a sandwich structure for breakfast this morning. Too bad. I should be inspired. Every time I give sandwich structure notes, I should have a sandwich for breakfast. So here are some examples of sandwich structures that I kind of showed in the last class. It's consisting of something with a face sheet that's typically very stiff, and then a core that is less stiff. And so that inner core can be a truss structure, right? So here we have a truss. Also a truss with this honeycomb over here. This guy making the surfboard. The skateboard also is a truss. Here for your IKEA furniture, you have kind of veneers on the outside, like these thin laminated wood sheets that are a little bit stronger. And then this is like particle board in the middle. These prefab architectural panels, it's kind of like fiberglass outside, and then like an insulation, foam insulation on the inside, right? So foam insulation. All right, and so the basic idea is that we have high stiffness core, or high stiffness face sheets, I mean. All right. And what this provides to us is it provides increases in the capital D matrix, which relates how much this item will curve given some applied bending moment, right? Has strong implications for this capital D matrix. Right? And so it relates how much the thing will curve to the bending moment that you put on it. And that's kind of what we talked about last week Friday, so I'm not going to beat that to death. What I want to talk about today is how we would modify classical lamination theory and what assumptions we made in classical lamination theory that no longer hold, and kind of blow up the entire theory and everything that we derived in the first like 5 weeks of this class. All right, so here I'll talk about modifications to classical lamination theory. All right, so sandwich structures. Remember I had this guy here, right? This was the sandwich structure that I kind of like was showing before. Glass epoxy face sheets, and then this like medium density foam on the inside that gives it this sort of sandwich structure. What you notice about this structure is it's like 3/4 of an inch thick. All right, it's like very thick material here. That's a lot different than like the thin laminates that we had done before that were like super thin, right? So this is like, less than a millimeter thick, this guy that I have here. And when we were doing classical lamination theory, which is for like this thin guy here, we made an assumption that the material was so thin that there were no out of plane shear stresses. Okay, so in classical lamination theory, so CLT is classical lamination theory, we have assumed thin structures. And when we make that assumption about being thin, we more or less assume that it's in a state of plane stress. And when it's in plane stress, there are no stress components in the z direction. So no out of plane stresses. That means with our traditional coordinate system that normal stresses are equal to shear stresses in the z are equal to 0. This is your plane stress assumption, which if you had me for 3005, we talked about, right? Sandwich structures no longer thin, like I just showed, right? That big old laminate structure that I just had before, you can't make an assumption that that's thin anymore, right? So now, with sandwich structures, no longer thin. All right, that's like me in quarantine. All right, no longer thin. God, that was a good one. I'm getting old and fat, just sitting here doing nothing. All right. Because of this, you can no longer make the assumption of plane stress, right?
So here we will say that we could possibly have shear stresses in the out of plane direction. So these shear stresses are no longer zero. All right. I think the best way to illustrate this is with pictures, because pictures are nice, obviously. They're worth like 47 words or something like that. How many words are they worth? At least 47. All right. So pictorially, this is what you should be thinking in your head when I'm talking about this idea. So for this classical laminate, right, generally very thin. And we make this assumption that there are no shear stresses in the out of plane direction, right? This tau xz. So if I were to think about like trying to put this thing into shear, it's not thin enough for me to like slide it in shear. All right, if I thought about like I had some business cards over here. If I thought about like a business card, okay, it's like super thin, right? If I try to like shear this thing, it can't support any shear loading. It's not gonna deform in any sort of shear manner. I can't slide this thing in shear to sort of like support that loading. It's too thin, too thin. No, too thin. Been going on a diet too long. It's too thin. So it can't support that sort of loading. But when we go to the sandwich structure, yeah, okay, when it's thick, then we have this like side edge that's now available to support some sort of shear stresses. All right, so if I have a thick enough piece like this guy right here, it's getting like very thick composite structure, and I try to like slide, yeah, okay, I could, if I was strong enough, like slide this thing back and forth to provide shear stresses on this particular guy. All right, I have the space, I have the thickness on the structure to do so. So yes, tau xz is possible. All right. This assumption or loss of assumption alone blows up composite laminate theory. All right. We would have to basically go to like square one and rederive all the equations that we've derived for this class. And we could do it. All right. We've done it before. We could do it again. But I don't want to do it again. All right. Because going through that whole process again would take like another 5 weeks. All right. So I'll say because of this, you need modifications to classical lamination theory. The modification that we're going to do is called first order shear deformation laminated plate theory. Yeah. It's a long one. This is the most simplistic modification that we could make. Star Wars approved. The First Order. You guys are all nerds. You're all engineers. You've seen Star Wars. Come on. First order shear deformation plate theory. All right. If you want the technical term, I'll talk about this technical term later. This is a modification of the Kirchhoff-Love plate theory called the Mindler-Riesen theory, which is not something you don't need to know. All right, just first order shear deformation plate theory is probably good enough. All right. Now, the idea here for first order shear deformation plate theory, and I'll just talk about the general idea without deriving a lot of the math. All right. And when we think about our classical versus our modified theory, I have some pictures here that sort of show the difference. All right. So here is like a composite laminate plate for our classical theory. If we're looking at the cross section and thinking about deformation, here's like the original condition of the cross section, like some portion of the cross section. And with our classical theory, we assumed that this particular plane section remained plane, right? And it also had the same slope backwards sort of as it did forwards, if that sort of makes sense. And so because of that, there's no shear that develops at this particular interface. That's different than the deformation of this first order shear, where we're again looking at what is the cross section before deformation, and now what is the cross section after deformation. And we see here what develops with the first order shear is that this plane section still remains plane, but it no longer has its normal with the neutral axis. All right. So what do I mean by that? All right. Well, here's the normal to this particular plane, which is our assumed deformation plane. All right. The normal to the deformation plane in the classical theory would have no shear forming. All right, so we see just the slope associated with the curvature that comes from this laminate. All right, now we have a different angle that forms the axis and bending. And the additional deformation that we have there is the shear deformation, this gamma xz. All right, so additional deformation from shear. All right, it's not technically deformation quite yet, but it's change in the slope of the piece associated with the Uh-oh. Did you guys lose me for a second? I think I'm back now. I think I lost internet for a sec. All right. Am I good? Can you guys hear me? Yeah, okay. Recording's still good. All right. Lost you for a second. But we're assuming now that there is this additional shear that forms, and that basically this additional shear is formed, and it basically blows up the classical lamination theory. That's all you really got to know. All right. So this first order deformation theory starts to really sort of throw things off. All right. I don't have time to really discuss all the details associated with the new theory. The main takeaways are this. Is that one, during deformation, plane sections still remain plane. But the normal coming off of that plane is no longer aligned with the neutral axis. All right. So this concept alone just blows everything up. All right. Interestingly, the A, B, D matrices can still be calculated. As previously described. And have same general physical meaning. All right. So that means the A matrix relates longitudinal tension to the strain that develops in the longitudinal direction. The D matrix relates bending moments that you apply to the piece to curvature that develops inside the piece. All right. The B matrix is the coupling matrix still. I still can load this thing in tension and have curvature that forms, or I can still load it in bending and have elongation from that particular expression, but it's going to be different because not only do you have sort of like this coupling between, in the B matrix, let's say bending moment and elongation, but you could also have another type of coupling, which is like bending and creating shear inside your piece, which really like sort of complicates things. But the same general ideas of the ABD matrix hold, but cannot use the following equation to relate loads and strains. You can't use this anymore, which we have used in the past. Okay, no longer good. All right. So this is really where we start to first see the deviation from classical lamination theory. You would have to include additional shear components into the strain vector on the right-hand side here for shear strains. All right, so it complicates things. All right, so that's no longer good. It's gone stale, baby. It's like bananas that have been in the bowl for too long. Stale. All right, the first order comes along and says, nope, these are stale. All right, last thing is, and I'm not going to talk about this, transverse stiffness matrix emerges. Relating transverse loads to shear strains. All right, it kind of looks like this. Transverse loading, we typically give the letter capital V. Equal to, here we have a stiffness matrix that looks like kind of like the A matrix or the B matrix, but we call it the capital C matrix. Clever. Related to shear strains, gamma XC, gamma YZ. Right. So relating transverse loads, which would be like if I were to put a load across my plate like this. Here, this is like a transverse load V. Should have talked about this in your statics class. All right. So my transverse load's V, and I could have those, you know, in the X or the Y direction. So we have a stiffness matrix that sort of emerges that looks like a relationship between applied transverse loads and shear strains which might develop. All right. So that's all I'm really going to say about the math. All right. I wish I had more time to like talk about it, maybe do some examples and show you what this really means. But I just want to like bury into your brain that when it comes to sandwich composites, you can no longer use classical lamination theory. And if you go into industry and you're trying to use classical lamination theory on sandwich structures, you can get yourself into a lot of trouble because you're under predicting some of the deformation and some of the loads that you're going to have if you're not accounting for the shear loading that occurs. Right. So if you want like more reading on this, there's a little bit more in your textbook for the class. And that's Daniel's page 194 to 199. Because I know you guys all have the textbook for the class, right? Yeah, right. Exactly. The classical lamination theory that we've talked about has a more formal name. So classical lamination theory is also known as the Kirchhoff-Love theory. And that's a general plate theory. And this is what we derived classical lamination theory from. Actually, classical lamination theory is a more complicated form of Kirchhoff-Love plate theory, but this is kind of the general form. We did an orthotropic form with classical lamination theory. And then if you want the first order lamination theory, you want the Minlin-Risner theory. If you go to graduate school and you talk about plate theory, you'll talk about this. All right. if you ever heard of like Eulerian beam theory versus Timoshenko beam theory, this is like an equivalent. All right. So Kirchhoff love theory, this is like Euler beam theory. I'll put like quotes around it. It's similar in style, and this is similar in style to Timoshenko beam theory. The beam theory was first, and then these guys modified beam theory for plates. All right. So if you ever need more additional reading and you want to dive in more on mechanics, there you go. All right. So this would be like for sandwich structures. So first order lamination theory, Mindler-Risner and Timoshenko beam theory. There you go. That's all I'm going to say about mechanics of sandwich structures. I wish I had more time to talk about more sandwich structure mechanics, but truth is it would take probably a week or so to dive in on it and get all the formulas correct, really hammer it home. And I'm done with the math in the class. All right. I want to give you some more practical stuff on the back end of this class, like how do we make sandwich structures? So that's what I want to do now. Okay. Okay. Yeah. So that's end of discussion on mechanics. So away we go now with manufacture, the better and more important part. All right. When it comes to manufacturing sandwich structures, the biggest issue is the interface between the core and the face sheets. All right. That's always the biggest problem when you're talking about sandwich structures. It's like always super weak between the face sheets and the core. So how do you buff up that core? How do you make sure that the interface between the face sheets and the core is solid so that when you go and you use this in application, it's not just going to separate from each other? All right. And for manufacturing these sandwich structures, there are actually many methods. And it really depends on face sheet and core. All right. If you have an open-celled foam, you have a different pathway for manufacturing than if you have a closed-cell foam as your core. Okay. An open-cell foam, for you people that are unaware of this, if I put pressurized air on one side of an open-celled foam, it would pass through to the other side. All right. For a closed cell foam, if I put pressurized air on one side, it does not pass through to the other side. So what does this mean for like manufacturing? Well, when it comes to manufacturing, if I manufacture a sandwich structure with an open cell core, that means that resin can penetrate into all portions of the foam. If you're manufacturing a composite and resin is penetrating into your foam and getting into your foam, you're going to increase the weight of the foam significantly and basically reduce all the benefits of your foam core in the first place, because you want that core to be lightweight, full of air, to really just displace the face sheets to the outside. You don't want that core to be full of like epoxy resin, which is a brittle material that is giving you just a crap load of weight. All right. So the point is, whether you're manufacturing something with a honeycomb cell, something with a truss, something with a closed cell foam, like all the manufacturing is going to differ based on more or less what is the structure of your core. All right. So it really depends on the face sheets and the core that you have. I'll give you the main ones that are often discussed in literature, though I will say that there are a lot of crazy manufacturing techniques for sandwich structures that I've kind of like seen personally over the years. All right. So for continuous fiber, plus epoxy, face sheets, and most general cores. These are the processes. All right. The first main one is just liquid molding. Second would be secondary bonding. We've already kind of talked about that a little bit. The third main one is CoCuring, with or without an adhesive. And then 4 is continuous lamination. All right, so these are the 4, and we're just going to briefly talk about these 4 methods. I think probably easiest for me to just talk over the slides here, because pictures are best. All right, so here we go with liquid molding. And you've kind of already seen liquid molding from the 429 class when you talked about resin transfer molding, because resin transfer molding with a foam core is one methodology for manufacturing foam core composites. So this is a picture that came from the manufacturing slide deck that I gave in 429. This is an RTM process, and you see here that this RTM process is actually for manufacturing a cored material. All right, so here is your core material. It's kind of like outlined here. And on the outside, you see all these. This is where your reinforcement would go on the outside. Okay, so this is kind of a dry manufacturing process where you place the core inside of the mold and it's surrounded by dry fabric. Then you inject your liquid molding compound into the mold to sort of solidify the resin in the fibrous region, which is kind of the outside dry portion of the core. All right, so that's the general idea here. Usually used for Vardum, RTM, resin injection molding. So you're moving liquid through your mold across the fibers, which are laid across a core material. All right. So dry fabric laid on core materials, then the entire assembly is infused, just like what you see here. So unlike honeycomb structure, if you try this with honeycomb, then your core, if it was honeycomb, would just fill up with the resin. All right, so you need your core to be like a closed cell structure. So it required a closed core material. So like a closed cell foam or a very dense wood that does not allow liquid to penetrate into the core if it comes in contact with it, right? So closed core kind of required here in this particular situation. All right. Absorbed resin, extra weight, always bad in composite manufacturing. So good cores for liquid molding might be closed cell foam, dense woods, etc. Bad core materials for molding, open cell foams, honeycombs. All right, if you have an open cell foam, then the resin is just going to penetrate into that foam and give you a significantly heavier core than what you want. All right, honeycomb structure, like you could just fill the honeycomb spaces with resin and then you just have a super heavy core. Like what is the point of that? All right, so you can't really use this process for anything that has open cells in the center. Right? All right, the second that we'll talk about is the secondary bonding process. And we've talked about this already a little bit. And this is probably the most traditional method for making sandwich structures. Maybe CoCuring is a little bit more common, but they're related anyway. So here's your secondary bonding idea. Here you have composite face sheets, which are manufactured separately. So you have flat sheets, or they don't necessarily have to be flat. They could be curved, but they're going to be applied to some sort of core structure. All right. So you manufacture the face sheets separately. So here, we've manufactured this laminate that I hold in my hands right here. This could become a face sheet for something later. All right. So it's the idea of you're fully manufacturing your face sheets to be used later in a secondary bonding operation. That's why it's called secondary bonding. You bond it secondary to the primary manufacturing. All right. So you manufacture these face sheets separately, and then you apply an adhesive between the cured face sheets and what will be your core. So here we have a honeycomb core, for example. And then with additional time, heat, and pressure to cure the adhesive between the two, you end up with your final sandwich structure, which looks like this. A majority of sandwich composites are actually made. So I would say most of them are made in this method, though CoCuring is also right up there. All right. So these face sheets usually fully cured, but maybe partially cured. Why would we want to partially cure them? Well, if you have some residual moieties, some residual chemical species left over in your face sheets, then you're going to have a better bonding with this adhesive and ultimately with the core that you have. All right. So how do we get to 80% cure? Well, good thing we talked about cure kinetics and you know how to do that. All right. So remember when we talked about cure kinetics, we talked about these like secondary or advanced manufacturing techniques with secondary bonding, co-curing, all those sorts of things. So this is one place where you might want to do that to increase the bonding between the face sheets and the honeycomb structure. All right. So then the face sheets bond to the core materials with an adhesive. And I'll say this, usually the adhesive is not the same material as the epoxy that's in the composite, right? So sometimes adhesive is same material as composite matrix, though not often. And that's because usually the matrices used for composite manufacturing are generally brittle and high strength. And then the adhesives that are used to bond the composites to the honeycomb are generally like lower strength, more ductility, have a little bit more malleability to them so they can absorb energy at the interface when you have, let's say, fracture that propagates between the face sheet and the honeycomb. All right, so a lot higher energy, a lot higher G1C values for the adhesive between the face sheets and the honeycomb. All right, so typically the adhesive here is not the same as the composite matrix, though sometimes it is. All right, so has to have a high toughness to sustain that shear loading at the interface should it occur. Okay, so if I like provided shear in this general direction, that adhesive has to hold that loading that I'm applying with that sort of shear force. All right. And we know the brittle epoxy matrix is, not so great for that. All right. Number 3 is co-curing. And co-curing, it's different than secondary bonding. Okay, so in secondary bonding, you manufacture the face sheets separately and then bond them on with an adhesive. For co-curing, you're basically applying pre-preg to the core materials and then curing everything together. So here's a picture example of this co-curing process. And I particularly like the series of images that I found in this paper because it sort of explains the process very well of co-curing. So here's the general idea. These people made this like thermoplastic material core. I think they 3D printed this actually, which is kind of cool. So this looks like polycarbonate, I think, but I'm not sure. Oh, it's a thermoplastic. Some thermoplastic polycarbonate could be a possibility. And then here you see like prepreg carbon fiber, which is being draped over the thermoplastic core. All right, so here's the truss core design. You can see it in a little bit more detail. And here's the layup in actuality. So you see the carbon fiber prepreg that's laid over that thermoplastic core truss. And this guy here, this is a vacuum port. All right, so that vacuum port, that's where you would attach the vacuum line to get into the vacuum bagging. All right, so this is before vacuum bagging, and you can sort of see that vacuum port there. So this here is where the vacuum port's actually coming in. And so what happens is you put this entire layup inside of this vacuum bag, and you put here all this white is bleeder cloth. Here, this yellow is vacuum tape. And it's all surrounded, you can sort of see the plastic here. It's all surrounded by what would be the vacuum bag. All right, and so what happens is this goes to an autoclave and gets connected to the vacuum. So you see the vacuum line here being connected to the vacuum port, and it's going to suck all the air out of that and compress the atmospheric pressure after sucking all the air out down onto that truss structure. And so you've got this face sheet that is prepreg carbon fiber that will be cured in the autoclave alongside of the core that is the truss structure. All right, so this is an example of co-curing because you're curing the carbon fiber directly onto the core itself. All right, that's a co-curing of a sandwich structure. So in this particular situation, I'll just bring this in here. Here's your co-curing information. sometimes called pre-preg or wet layup method for obvious reasons, obviously, because you're applying pre-preg or wet fabric right to the core material, and pre-preg placed on core and cured in presence of core, capable of withstanding manufacturing temperatures and pressures. All right, so if I wanted to use a PLA core material, I'm gonna have a bad time if I'm bringing that up to temperatures of like 100 C. All right, so the glass transition temperature of PLA, for those of you with polymer background, is about 50 degrees Celsius. If I take a PLA core and I expose that to 100 degrees Celsius, that thing ain't going to last. All right. So you have to make sure that if you're going to use this methodology, that whatever manufacturing process is required for the face sheets, let's say you're curing at 150 C under 3 atmospheres of pressure, that your core can handle that. All right. If your core is just going to get crushed, then that's a terrible manufacturing idea. All right. We'll use this vacuum bagging or out of autoclave compression molding techniques. All right. So autoclave or out of autoclave techniques or compression molding techniques like hot pressing. All right. So most common technique for parts with cure surfaces and truss structured core. So think about like a small model of a canoe, right? So a canoe might have a truss structure and you're laying over some wet pre-preg and you're putting that in an autoclave to co-cure that together. All right, the small canoe model maybe. The truss structure that I just showed on the previous slide, that's a good idea showing like the drapeability of the pre-preg over the what would be the truss structure in the core there. All right. So this is the example honeycomb truss structure from that I was kind of trying to show. So again, the pre-preg laid directly on the core and cured together in the autoclave. So that's co-curing. All right, and then the last is continuous lamination. And continuous lamination is a high volume production. All right. So this is high volume production. Most of these other methods that I kind of showed were sort of one-offs. All right, this pre-preg truss structure, if I have to make 1,000 of those, god damn, that's going to take forever. All right, so not a very good methodology for making like a high volume production of these pre-preg truss structures. All right, instead, if you want high volume, you want the continuous lamination process, and the general process would look something like this. And sorry about the terrible image, but it's kind of like the best image that I found about the continuous lamination process. It just tells you what you need to know about continuous lamination in one picture, even though the picture is like terrible. All right. So core material coming in, and there are face sheets, face material that's being applied. So you see that being applied to the top of the core, and then it goes into an oven / pressure cooker where the face materials are being cured in the presence of the core. So this is kind of like a co-curing process, but all in one sort of assembly line. And then out the back end, you have cutting these continuous pieces over and over and over and over. Okay. So that's the continuous lamination process. It's for high volumes. It's got like flavors of pultrusion to it, right? So remember, pultrusion was like continuous fabrication of composite cross sections. So we make I-beams, we make diamond-shaped cross sections from pultrusion, so on and so forth. So good high volume production method here for continuous lamination. And this image is a very simplistic image, but in reality, this continuous lamination process is enormous. All right, so it takes lots of space. All right, so like warehouses full of space. And I like this picture. It's a good example of a continuous lamination line in China. One of the rare times that you get to see into manufacturing of Chinese goods. And they're not actually manufacturing anything. They're just kind of showing a picture of the plant. But the idea is that the continuous lamination line is here. And so you see that this is tens of yards long, if not as long as a football field, so 100 yards. These vats here look like the vats that will be used for the polyurethane core. Okay, so those vats there, it's like part A is contained in one vat and part B is contained in the other, and part A and part B are mixed together to make the polyurethane core. And then this here looks like a bunch of, I shouldn't be using red, maybe I should use Blue come through a little better? No, it's not as good either. All those barrels there, those look like barrels of precursor. So precursor epoxy components. So liquid epoxy A, liquid epoxy B. That's what that kind of like looks like to me. So I imagine you're kind of starting over on the right-hand side here with fibers being fed into this production, and then the polyurethane core is coming in somewhere down here, and it's being mixed and manufactured. That becomes the core material, and then maybe somewhere down here down the line you're adding the epoxy to the fibers on the outside and kind of making this whole thing kind of come together in this continuous process. I don't know for sure. I'm just sort of spitballing and guessing, but if I had to guess, that would be kind of like the idea of how this continuous lamination process is actually working in reality. All right. So those are your four main manufacturing methods for sandwich composites. But like I said, there are a lot of other crazy techniques that people have used in the past, but I'd say they're all variations or variants of those general ideas. All right. Last thing I just want to give you a touch on in sandwich composites before we go is how you might evaluate the strength of the interface between the face sheet and the core. All right. Because the sandwich composites have their own crazy theory, which is this first order lamination theory, the math behind evaluating the strength of the interface is actually crazy complicated. All right. You're talking about shear stresses that are developing an adhesive at a very thin layer between two different materials that behave completely differently, right? So a core material is going to have a very different response than the face sheet material because they have crazy different stiffnesses. So you have an adhesive that's bonding a weak, less stiff material to a very strong face sheet material. Like, the math that's going on at that interface between those two is intense, all right, especially since they're orthotropic. All right. So I don't have a lot of time to get into this idea here, but I'll say the most common test that's done in industry to evaluate the strength of the interface is what's known as the short beam shear test. All right. And with the short beam shear test, you make a sample that is very short. All right. So the idea here is that you have a 3-point bend sample with a short span. And what happens when you shorten the span is that the bending is minimized and the shear is maximized. All right, so why the fuck did this go all the way over there? All right, so this is what I want to show. So here, this is a short span length 3-point bend. The shorter that you make the span length, the more that the shear is going to be maximized. And you can draw yourself a shear diagram to sort of confirm that. Basic idea is that there is a standard that exists that discusses this short beam shear test. So you can see with short beam shear testing that the failure is going to be at the interface, sort of between the face sheet and the core. So there's some pictures here of some samples that I had worked on in the past, just going to kind of show quickly, that highlight this general idea. So here's a short beam shear test kind of on the left-hand side, and we have carbon fiber face sheets and a balsa wood core here. And what you'll notice is that there's some transverse shear that's going on in the core. You see this like 45-degree angle indicating that there's shear present. And you can sort of see the delamination between the core material and the face material. It's highlighted a little bit more in this image here on the right-hand side, this face sheet delamination. All right, so this is typically how these cord composites will fail. And so I just wanted to show you this short beam shear test because it's the most common test that's used in industry to describe the strength of the interface. All right, you load this up, load this up, load this up, and then there's some load value at which this thing fails. And so you can compare the maximum load value of like one composite to the next with this short beam shear test. And obviously the sample that has the highest load has the best interface between the core and the face sheets. So there are some standards associated with short beam shear testing that I've uploaded to Blackboard, and I'd urge you to look at those standards and at least be familiar with them if you ever need to use them in industry in the future. All right, so here's some excerpts from some of those standards, and you want to be scared with a lot of algebra. Here's the algebra associated with some of these short beam shear tests, and we see a lot of crazy complication that comes in here because the core material is different than the face sheet material, and we have this shear correction for laminated sandwich structures and so on and so forth. So the standard tells you how to do all the analysis, but the derivation behind all of the stuff that pops up in the standard is crazy complicated, and we just don't have time to do it. So thanks for sticking with me today, an extra 2 minutes. That's going to be it for material for the class. We'll do a review on Wednesday. So make sure you take a look at the review, and hope you guys have a great day. Thanks for coming.